the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
So thanks, Stevens, for having me, and thank you to all the sponsors, to Hugo New and all of the sponsors for this series. I know I've attended a few of the lectures in the past and always been really impressed with the quality and interesting range of speakers that you've had. So I'm excited to talk to you today. I'm hoping I can bring a little insight into the work that I do, hopefully pique some interest into some of the fields that some of the participants are studying or considering pursuing in the future, and hopefully spur some interesting discussion. I do want to say that probably each of the topics I discussed today could be their own, at least a full day of presentation. So if some of these pique your interest, please do feel free to reach out or do some more research on your own. I got a really nice introduction already, so I don't need to introduce myself, but to talk a little bit about what we'll be covering today, we're going to be talking about the contaminated landscape that we all live in and that people in my industry work in, about how did we get here? How did New Jersey become the Superfund capital of the world? What is the Superfund program? How do environmental cleanups happen in the real world? Are they green and sustainable? Are they not? What could be done to make them more sustainable so that we're not only improving our communities by doing remediation, but doing it in a way that's going to be sustainable in the long term in the future. So with that discussion, I'll talk through the regulations that exist today and how they got there, careers that support sustainable remediation work in the real world, if you choose to go outside academia for your profession. Not that academia is not the real world, because there's a lot of incredible research going on that really supports all the work going on sites every day. And then the bulk of the presentation, I'm going to walk you through actually a real world example, anonymized to protect the innocent, but of how remediation works in the real world, how decisions are made, what kind of work is done to support the remediation of a contaminated site. And then I would love to have your questions. We'll have some discussions. And then I just want to preface this with almost all of the photos that you'll see in this presentation were taken either by myself or by others who work on my team, real sites throughout New Jersey. So you really hopefully get some eyes into how the work really happens, which is the thing that I love most about doing remediation work, is we're taking this very theoretical science, we're taking it out of the lab, out of the researches, and putting it really into the real world to make change. So how did we get here? As Professor Sarkar alluded to, we are in the Superfund capital of the world. New Jersey has the dubious honor of having the most Superfund sites out of any state in the United States, despite our relatively small size. It all started with the Industrial Revolution in the 17th and 18th century, right? People were eager to get energy, to build industry, to make money with new technology that was arising. And there was really no consideration at all of environmental impacts. It was, how do we get energy? How do we do it in a cost-effective way? If it meant dumping tailings into a stream, throwing waste out the back door, dumping things into a hole, polluted air, it really wasn't, there was no knowledge around what impacts this might have in the long term. And this went on for several hundred years. And really, knowledge about environmental issues started to come into the public realm in the mid-20th century. I'm sure a lot of you have potentially read or at least heard of the book Silent Spring, which sort of brought to the forefront for many people in the general public that the use of pesticides was harming wildlife, and causing ecotoxicological effects to people as well. This started to cause some public outroar. And then another big case that really caused a lot of change was called Love Canal. And that's what the pictures on the right side of the slide are. If you're not familiar with the Love Canal case, this was an area that was supposed to be sort of an idyllic community in northern New York near Niagara Falls. It was built as this place where you could live out the American dream. You could buy a small home and raise a family. And one of the big industries that supported a lot of the people who lived there was a chemical manufacturing company. And it was called Love Canal because there was a canal that was going to be dug through this community that was going to provide power and water. The canal project really never was completed, but the excavation for it started. So this chemical company who employed a lot of the people in the community realized that it was a great opportunity to get rid of the waste that was generated at their plant. And so they started drumming up their wastes. They put them in this big hole that was excavated for a canal, and the hole got pretty full. They actually did something that was pretty revolutionary and responsible at the time, which was to put a little cap over the top of it so nobody would touch the chemical wastes. And the community was really healthy and it was expanding. And so they actually the community was looking for a place to build a new school. And they were looking at taking this landfill property through eminent domain. And the chemical company said, wait, we have a great idea. Rather than the government taking this through eminent domain, we're going to essentially donate it to the school district for $1. And they wrote a legal agreement, and there were just a few sentences in that agreement that said, if there are ever any problems or environmental issues that come up related to this property, it's the school district's problem. And the school district said, great, thank you for the donation. They took the property, they built their school, they cleared some of the land, and things kind of continued as usual. Until one spring, it was very wet. There was a lot of rain. Kids were outside playing after a long winter, and they started coming home with chemical burns. So their eyes were itching, and people started getting sick in the community. As the meltwater was getting really soggy, people were seeing drums coming up through the ground. One thing led to another. Local elected officials were informed, went all the way to Washington. And long story short, the whole community was actually condemned. People had to leave the houses that they'd owned and the communities they'd formed and moved away, many with long-term health problems. And this case led to the formation of CERCLA, which is also known as the program that led to the Superfund program, in which the federal government in the US can step in and perform remediation of a contaminated site when there's no responsible party available. So the remediation of this site actually was completed, I think, in 2004, and there's still long-term monitoring going on. So to give you an idea of the timeframes here, obviously the people who lived there were potentially impacted for their whole lives, but the remediation process took many, many decades to address. But it's not just ancient history, right? To bring us into the modern day, the US EPA was formed in the 1970s, as well as many regulatory agencies in specific states or other communities. The New Jersey DEP was also formed in the 1970s. The environmental regulations started out pretty limited, and obviously they developed over time, coming more into the modern era, into the 2000s. New topics kept coming up, as well as old topics being refined and improved. In the 2000s, people started to become, or I'll say the regulators started to become more aware of the concept of environmental justice, that these contaminated issues that are so common across much of New Jersey and the country are more often in communities that are not well represented in government, that have people of color or minorities, and they don't often have a say in where these facilities are sited. Another topic that came to light in the early 2000s was PFAS, or emerging contaminants, which I think probably most of you have heard of, right? The forever chemicals that are in land and water and air, no matter where you go in the world. And so regulations started to form very, very loosely around these topics in the 2000s, and a lot of research was done. Moving into the modern day, the regulations on these topics are still evolving. There's now an increased focus on the effects of climate change and sea level rise on our communities, and how that dovetails together with all the existing regulations around cleanup and development of contaminated and non-contaminated sites. I'm sure as we've all lived, the frequency of these storm events is increasing, and the effect on all of our communities is very great. So we, particularly in New Jersey, live in an incredibly regulated environment, and not every state and not every country is like this. But if you work or you live in New Jersey, there are essentially rules to do everything. And so the work that I do as a consultant and my peers do in this field is governed very significantly by the regulations that are made by government officials. Bringing us to like, what actually is the work? That's sort of a question I get a lot when I talk to students or others outside the consulting industry, is like, what actual jobs exist in this industry if I want to help the environment? Obviously, there's a lot of work in research and academia. There's a lot of important studies going on around, for example, remediation of PFAS. How can it be done? What are the different technologies out there? You know, any different remediation technology, there's a ton of research to be done, or many other environmental topics as well. Outside of academia, though, there also are a huge number of jobs in different fields. Government regulators and politicians are responsible for drafting and passing the rules that essentially govern how all of this work happens in real time. Consulting professionals such as myself handle the engineering, the environmental design, the geology and hydrogeology and sustainability aspects of these projects. We're supported by analytical laboratories who are taking the samples that we collect in the field and providing analytical data that has the appropriate QA/QC so we can make decisions based on real defensible data. We're supported by contractors who help us do the actual work we need with the heavy equipment in the field. And then we have partners in the nonprofit community and NGO sector. And throughout this, we're constantly interfacing with environmental and non-environmental attorneys who are helping to really make the documents that govern how all of our work is done. So I like to say that being a consultant, you wear a lot of hats and you sort of need to understand how all of these things work. Some days you're doing science, some days you're doing engineering, some days you're doing lawyer, you're sort of a lawyer, you're doing a little bit of finance, you're understanding what the latest technology that's coming out of research papers is. So you get to do a lot of different things and you can choose a niche that's interesting to you. And so then where does this leave us when you get to really the specifics of a contaminated site, right? Most sites are not the Love Canal where you're going to spend 50 years performing active remediation, but it's not a quick process. I've put on the slide here sort of a typical life cycle you might expect of I'll say a site with a medium amount of contamination. It's not the cleanest place you've ever worked, but it's also not a real catastrophe, right? You usually spend the first year conducting research and assessment, understanding the history of a property, and doing some initial sample collection to determine the magnitude of the problem. After that, you'd spend anywhere from 1 to 5 or more years determining how significant any problem you might have found is, right? Is this a small problem that's isolated to a little spot at the back door, or is this a significant problem that's impacted a whole community? Depending on the magnitude of the problem and the complexity, this can take quite a long time to complete. Once you have a handle on what the magnitude of the problem is and the extent, you can develop a plan. How are you going to remediate it? What's practical? What's cost effective? What has just basic scientific principles that will work? And that's a match for the setting and the geology you're working in. Implementing a remediation is sometimes a fast process of maybe a few weeks, a few months, depending on the complexity. It also can take several years, really depending on what you select. And then many remedies don't just end when the heavy equipment leaves the site. There's often long-term monitoring and maintenance requirements that sometimes go on in perpetuity. And so to make this as I was working through developing some slides for this, I thought, how can I make this more tangible, more interesting? And so what I want to do today is actually take you through a real project that I worked on a few years back. Now I'm going to take you through each of these steps that I just outlined. What did we do? What did we find? And how did we make our decisions? So we always start out with an initial assessment. And this is a part where it helps to sort of put on your business hat. Because every project starts with a person or a company. Well, and every company is made of people, and they have a goal. And most companies' goals are not to clean up a site or to be sustainable or to do something good for the environment. Most companies' goals are to make money, to sell a property, to buy a property, to build a building, or to create a product, right? So you need to start with your client and understand, why are you doing what you're doing? Did you get a violation from a regulator? Do you want to sell your property? Do you want to build something new? And once you understand what they care about, you can say, okay, I understand your goals, and then I understand what needs to be done under good scientific principles and under the regulations, and I can put those two things together. At that point, then you start to look at, where is the site? what is the soil? What is the geology? What do they do on the site now? And what was done on the site a long time ago? Are those two things the same, or have things changed over time? We do a lot of research into prior environmental investigations, often reading documents that were written 10, 15, 20, 30 years ago to understand what was found then and how does that relate to the conditions of a site now. And then once we've done all of this research, we go out and we physically visit the site, we perform careful inspections, and that sets us up well to understand what, if any, sampling might need to be done on a property. So to walk through some of those steps in more detail, we almost always start with geology, right? We're all on top of, in New Jersey, in most cases, there's some superficial soil, and then you'll encounter bedrock beneath that. On the slide, I've excerpted a portion of the geologic map for the Patterson Quadrangle up in northern New Jersey. Pretty typical for what you'll see across a lot of the state. The geology is primarily a shale from the Jurassic period. It's a red-brown in color. You'll see some photos on my next slides. And this is important to understand because when contaminants enter the ground, the way that they travel and the way that they transform can vary pretty significantly depending on the geologic setting where you are. So contaminants travel through shale, which is very small fractures that are maybe not well connected, a lot differently than it might through, say, a basalt with massive fractures in which it travels quickly through a single pathway. Another resource we looked at are historic fill maps. Historic fill is a condition that's very common in New York and New Jersey, right? A lot of our states were historically low-lying, what we now call wetland, which might have been called swamp a long time ago. And when people wanted to build in these areas, they imported whatever kind of fill they could get, which often had debris and construction materials in it, which comes along with contaminants. And so in New Jersey, historic fill across the state has been roughly mapped out by the DEP. On the map on the right side, you can see some brown areas where the DEP says you should suspect that fill might be encountered. What we found specifically on this site is that we were adjacent to one of these brown patches on the map indicating historic fill, but not within the mapped area. So does it mean you're clear? I wouldn't say so. It might be a reason to keep looking. So we knew going into it, we should encounter bedrock of the Passaic Formation, red-brown silt as the overburdened soil, and potentially some historic fill material. We also look at a lot of historic resources that are available through either commercial database companies or available online or sometimes in paper or in-person file reviews. Here are some excerpts of some of these resources. On the right side, you can see a relatively modern day aerial photograph of our site. It's a warehouse building and a parking lot. There's not too much to see there. It's next to a railroad that runs to the east of the property. We're surrounded by some industrial warehouses and residential development to the south. But then we go back into some of these historical resources to say, well, we know what's there today, but what was there 10, 15, 20, 50, 100 years ago, right? So on the left is a historic fire insurance map. These maps can be a great resource to understand what was on a property. So in the modern day, our facility is used for manufacturing cosmetic products. In 1965, when we look at the map on the left, we can see our property was used as a sporting goods warehouse by Wilson Sporting Goods Company. Relatively innocuous use, doesn't raise a lot of red flags from an environmental perspective. But we also have to look at the surrounding properties because contamination doesn't just stop when it hits a property line. So we can see there was still a railroad to the east. Beyond the railroad, there's a property labeled Industrial Works. Okay, we go to the west of the property. We see there's a building labeled E.I. DuPont Warehouse. If E.I. DuPont doesn't raise a red flag for you, you should do some reading about environmental. They're a big chemical manufacturing company. So while a sporting goods warehouse doesn't really raise any big flags, an E.I. DuPont warehouse does. And then to the south, the bottom of the map, there's a large facility. It's not labeled. It's a little hard to see, which is often the case with these old maps. But what we can see, if you can see my cursor, there's down by the property line, it says fuel oil tanks buried. That's what these two rectangles are. We see that there's these rail lines, which are these two vertical lines. They seem to randomly terminate at the property boundary, which seems like a little strange, right? Why would somebody have gone to the effort of building a railroad that terminates in the middle of nowhere? If you had the original copy of this map, you could zoom in and read some of these other features, but there's a boiler room, there's oil tanks, There's a heater room, some transformers. One thing that caught my eye, in the corner of the building on the left side, it says hospital. There are not a lot of industrial facilities out there that have a hospital internal to them. It makes you question what could have been happening at this site in 1965 that somebody would be injured so significantly that they would need an on-site hospital. So we continue to dig into the files, right? But we can go back in these maps and images further. So before we were looking at 1965, now we go to the 1950s. The warehouse building is not there. The E.I. DuPont warehouse is not there. The facility to the south looks pretty much the same. And suddenly the mystery of the railroad is solved. The railroad line didn't always terminate at the property line. It actually ran all the way through the subject property, which is what we're looking at, up to this boiler house to the north. There's a switchboard building on our property over here. So you're starting to put together the pieces to say, oh, this was actually a much bigger facility. And when you look at the aerial from a similar time period, it becomes apparent that there were some access roads running between this large industrial facility to the south and the building that we're looking at, which is the modern day warehouse. So it doesn't answer a lot of questions, but it raises a lot of questions about what was being done there, what chemicals or hazardous materials were being transported, how were they being stored, were they being spilled, how were they being disposed of when their useful life was over? And these are all questions that we look to answer during the next phase of our work. So during the next phase, we come back to modern day, right? We can't time travel, unfortunately. So we're left to inspect and interview. In some instances, we go out to properties or we work with clients and they say, I've had somebody working at this facility for the last 50 years. And you talk to that person and they have a tremendous resource of knowledge of what's going on there. But more frequently, you run into somebody who said, I've worked here 2 or 3 years. I know what's happening now and I can walk you around the facility. And this inspection is as much an art as a science, right? You ask good questions, you listen to the things that aren't being said as much as you listen to the things that are. So as I mentioned before, this was a cosmetics manufacturing facility when we visited it in the early 2020s. A few photos from the site visit are on the slide. On the left, you can see outside the facility at the back wall, there was this pipe that came out of the wall into this gravel surface, and there's this big black stain on the ground outside of it. I don't think you need to be an environmental scientist to know that this might be a cause for concern. A few other photos I've included. Most of the operations were inside the facility, which had a really nice new epoxied floor. But then as they had excess fluids, most of them drained into the floor in a situation somewhat like the one you see on this photo. And the facility operator couldn't tell us about where any of the drains went. Additionally, we observed they were storing drums outside in their parking lot. It was pretty difficult to inspect much due to leaves and snow on the ground. So that leads us to step 2. What are we going to do? We've done all our historical research. We've looked at our geology. We've looked at as much of the old files as we can. There were a few old reports suspected there might have been some old tanks at the facility that weren't there anymore. We were worried about fill material. We were worried about adjacent operations. So what did we do? We did a lot of different things, right? And the objective of this work was to determine presence or absence. Do we have a problem or do we not? So we started off, I'll say, with non-intrusive activities, which are on the top of the slide. We sent cameras down all the drains to figure out, are the drains cracked? Are they old? Are they new? Are they in good condition? And where do they go? In the back of the photo, you can see that drain I pointed out on the previous slide. We scoped most of the drains and found they were in pretty good condition. There were no cracks, and largely they were concluded to go to the sanitary sewer, which was appropriate. Some we weren't able to scope with the camera, so we conducted dye testing where you put colored dyes down a sink and you see where they come out in different manholes or other locations around the site. In this instance, the green dye came out in a sewer manhole, which is what we'd expected, but I've worked on other properties where you pour green dye down a sink and you find it coming out a hill slope at the back of the property and running into a stream. We also conducted geophysical survey, which helps you see, using geophysical techniques, what might be underground, which helped us to locate some areas where tanks had been removed in the 1990s, where there was no surface expression anymore. Based on the outcome of these investigations, we were started to do intrusive work. We installed soil borings at the property using what's called a direct push rig. You slide a clear acetate sleeve into the ground using this hydraulic equipment you see on the left. You pull it up, you get what you see on the middle picture here under soil sampling. It's a cross-sectional view of the soil. which we'll go into on the next slide. We also conducted a groundwater investigation to look for what regional impacts might be present due to the surrounding industrial operations. So all of this is pretty collaborative effort, right? You have to be talking to the property owner, you have to talk to the people who work there, you have a team of contractors and staff, you've got a laboratory to coordinate with. Often we're talking to the attorney who's marketing a deal for the property. We may also be talking to financial institutions. So it requires not only a background in science or engineering, but an understanding of big picture. So we looked at soil first, which is usually where we start. If you remember on the geology slide, I said, we're in the Passaic Formation. We expect a reddish-brown silty soil. That top left picture is exactly what we were expecting. It's native soil from the Passaic Formation. This is a unimpacted historic fill, that we found in the corner of the property. However, as we progressed closer and closer to the railroad and what had historically been lower ground, we started to find historic fill material, which is what's in the rest of these slides. You can see white fragments are concrete. We've got black, which is ash and millings. There's little red pieces of brick. There were some bits of plastic and metal, obviously not deposited there naturally, and these impacts went down to about 10 feet below grade. We use this tool called a PID, or photoionization detector, which is in the top right. It detects volatile organics coming off of the soil. It's definitely not a definitive reading, but it gives you an initial field screening tool, better than using smelling soil. You don't want to smell something that's potentially contaminated. Based on the visual observations we make and the screening with the field tools, we select intervals and locations where we're going to collect soils for laboratory analysis. So our technicians out in the field collect up the samples, and we send them off to the lab to see what contaminants may be present. In this investigation, we found that the area of staining that was on my inspection slide was impacted with a number of petroleum compounds, because it was actually the condensate coming off of a compressor inside the building. We also found that the historic fill material that's pictured here has metals and PAHs, which are both very common contaminants in historic fill soils. We also sampled where some tanks had historically been located, and luckily we found there was no contamination there that exceeded the state's regulatory standards. And all of this work is done under the framework of, in New Jersey, of the New Jersey DEP. They've laid out a lot of specifics around the way that you do this kind of work and how you design a work plan. When you get into groundwater, it's a little bit more complicated, and it's a little, I think, harder to picture if you haven't done this before. So at the surface, a monitoring well looks like the picture at the bottom center. It's a pretty unassuming small manhole. You've probably walked over hundreds of them in your life and never noticed them if you weren't looking at gas stations and supermarkets and just places you go in your everyday life. But what you'll see underground is the cross-sectional view on the right. When we install these wells, we do it in a very specific way to target areas where we suspect or know that releases to the environment have occurred. The source area, which is indicated on the slide, is where you suspect the spill occurred. You want to install your well, and you put the well screen, which is the area where the water enters the well, immediately through that source area. So we're in step one, right? Determine presence or absence. And then we move to the next step, which is, once you know there's a problem, figure out how big it is and delineate it. And so that's what this diagram shows you. It's this iterative process in which you step out. So say you put in your source well first here, you may step out to the right, hoping that your plume is very small, and you find you're still in the core of the plume. You step out again, it's getting better, but you're still in the plume. You may have to step out 3 or 4 times until you find the end. And we're not only going horizontally in this process, but we're also going vertically. So you need to think in 3D to find not only the horizontal extent, but to go deeper and to find the bottom of the plume. And then to make this even more challenging, you're really thinking in 4D, because groundwater isn't a static feature like soil that just stays in one place. Groundwater is constantly moving and flowing at a specific rate, which is something we can measure. And so you need to think about, if you suspect there was a historic release of the property, is that contamination still in the place where it was released, or has it migrated or expanded into other areas? So these two diagrams provide you both an overhead view of how this process might go, as well as a cross-sectional view. And this, installing an initial monitoring well might just take a day. You come back and you sample it a couple weeks later, you have a result. It's a definitive answer from a lab. There is or there is not contamination there. But this process of designing the monitoring well network is relatively complicated. It's expensive. It requires a lot of coordination. So it's something we do with a lot of care and caution and design. On the site that we're talking about today, what we found with our monitoring wells is that thankfully that stained, yucky looking area at the back of the site was a relatively recent discharge, and it hadn't migrated down to the groundwater because it was very superficial only in nature. But what we did find was there was a significant source of chlorinated solvents in the groundwater. And this didn't make a lot of sense at the site because there was no site history of using the specific solvents we had found at the site. So it led us to believe that there might be an offsite source of the groundwater contamination. So we look at a lot of different lines of evidence to make that determination, right? We say, like, is there a trend if you install multiple wells across the property? Are you highest in the center? Are you highest on the edge? What direction is the groundwater flowing? Is there a specific chemical signature that you can pick out of the analytical data if there might be more than one plume that is overlapping another? So this is a pretty complex process. Again, you could have a whole day seminar on just how to do this. But I'll move on because I could be here all day talking about groundwater delineation. So throughout this process, right, we're collecting soil, we're collecting water, we're talking to people. But the whole time you have to keep in mind, the ultimate goal of this is to protect human health, to protect the environment, and to make sure things are being done safely. And so we call that evaluating receptors. A receptor is a sensitive use population, whether that's a school, a childcare center, just a person breathing indoor air, an ecological receptor like a wetland or a stream or a habitat. So in particular at this site, we were concerned about solvents in the water. So if you think about if you've encountered a solvent in your everyday life, or even if you've used a Sharpie marker, when you pull off the lid, there's a smell, right? So that smell is a vapor that gets into the air. So if you're in the groundwater below the surface, the vapors come off the water. If you're sitting underneath a building, they often get trapped underneath the slab of the building. And depending on how much contamination is in the groundwater and how your building is constructed, your vapors have two choices. Either they go around the building and up outside, or they come somehow through the slab or through a crack and they get into the air. And that's when indoor air can be a problem. So we sampled two things. On the photo on the left, we're collecting a sample from the air beneath the building slab. We've actually drilled a hole through the floor and we're sampling that in that metal canister. And then in the photo on the right, we're sampling the breathing air inside the building. In this case, we found that there was carbon tetrachloride in the groundwater, in the soil gas beneath the building, and in the indoor air, showing that the contamination in the water is actually getting into the indoor air that people were breathing. There's a lot of different ways you can evaluate this. In our instance, we were able to use some modeling tools to evaluate how the building construction and the contaminant concentrations and the soil all came together and what exposure level that would lead to for occupants inside the building. And this is just one very specific example, right? If you're in a site in an ecologically sensitive area, that's an entirely different avenue to look at. If you're working at a school where there's kids occupying the building and playing outside, you have a whole different exposure pathway. So you have to be thinking about this throughout the process and continuing to revise your understanding as you start to understand how big is the problem and where does it go. The other piece you need to think about is your site setting, your climate risk, and any other risks that might apply. So in the case of our sample, we're in a pretty upland area in northern New Jersey. We're not near any streams. We're not in a flood hazard area. We're not near a wetland. But that's not always the case, right? Much of New Jersey, especially, is in coastal areas or in fluvially flooded areas. On the bottom, I've excerpted a cross-section that sort of explains how this is viewed from a regulator's perspective. But I think it also provides an interesting way to look at it as a scientist, right? You might think to yourself, if you start on the right side of this graphic, you're at the current sea level. Mean high water line puts you right here. So an uneducated person might say to themselves, they could safely build right here next to current sea level. We all know that's not the case, right? Sea level rise is happening, whether we like it or not. So the distance between the current sea level and the projected future sea level, it varies, but we call that the inundation risk zone. It's not a safe place to build. And FEMA, which is the federal agency that regulates this, has further put a limit to say, not only do we need to account for our sea level, we need to account for what happens during flood events. So they regulate what's called the 1% chance annual flood, also called the like 1 in 100-year flood, to say that 1 in 100 years is an acceptable risk to build above. Now, whether or not a business or a person thinks that's acceptable, that's their choice. But generally, 1% is considered to be the standard. So under the FEMA rules, the 100-year flood line is at the second arrow here and says you could build a house where it is, or a building where it's shown on our graphic. Now, New Jersey actually just this year already published new rules called the PACT rules, or Protection Against Climate Change, stating that New Jersey recognizes that we have a particular risk for climate change due to the fact that so much of our state is in coastal areas. And New Jersey has applied a safety factor of 4 feet above FEMA. So whereas FEMA says that you could build your building in the location shown on the graphic, in New Jersey now in 2026, you actually need to go 4 feet higher up a hill to be in a location that the regulators in New Jersey and the scientists who supported that study believe is safe to build, given the risk around climate change and the increasing level of significant storm events. So what does that mean for people or businesses who own homes in low-lying areas that were built historically? It doesn't mean people need to demolish their homes immediately, but it means for rebuilding and for new projects, there's safety factors involved, and in many instances, structures are being built on stilts or grade is being raised before building new structures. So we have to think about this throughout the process, and it ties pretty closely to remediation because often remediation and construction are performed at about the same time. So when we have all this information, right, we've collected a lot of different things, and a lot of these data points individually don't mean very much. So once we've collected all this information, we know how far contamination goes, we put it all together into something called a conceptual site model. This is both qualitative and quantitative. There's like a cartoon on the right that sort of tries to put it all together, right, into one idea. You're looking at how did a plume get to where it is from the source? How is it impacting people or the environment, right? Is it going to a stream? Is it going to a house? Are people drinking the water? Is the contamination coming up in dust or vapors? Are people touching or playing or doing construction in the soil? Is there ecotoxicity for animals or wildlife? So this model looks to put it all together and identify where the biggest risks are. And based on that model, we put together our work plan. We look at number one, what's going to be most effective and what's going to mitigate the exposure. And then I will say in almost all instances, the second factor you look at is cost, because you can have the best remediation strategy that's going to do the greatest job, but if it costs 10 times as much as something that would maybe be not quite as good, usually people will go for the not quite as good option because money is a factor here too. You look at what the long-term effects are going to be, if there's long-term controls needed on a property, if there's mitigation needed off-site. And then sadly, I think sustainability in the real world is generally the last thing people look at because they see effectiveness, cost, exposure as non-negotiables, right? They're regulated very significantly. Cost is obviously an important driver for business people. But in most businesses, sustainability is not top of mind. I won't say for all, but for most. But what I have seen over the last, I'll say 5 years is increasingly people are more interested in looking at remediations that have a sustainable option. And in some instances are willing to spend more money on that. So what are sustainable remediations versus not sustainable remediations anyway, right? So the ITRC, which is an agency that works across the United States that does a lot of great research, put together this graphic on the right, showing that sort of in an ideal world, environmental, economic, and social pressures all come together to make a green and sustainable remediation. I think the reality of how this works currently in most instances is environmental pressures and economic pressures come together, and like maybe the social pressures are out there like floating off in some other world that's not very closely connected. Most state and federal agencies encourage but don't require sustainable remediation. A lot of, I'll say, more corporate entities that are doing remediation are motivated by sustainability goals. So if it's economically feasible, they're interested in doing it. So some of these things can mean monitoring water usage on a project or selecting a remedy that uses less water or has a smaller carbon footprint, right? So instead of running your waste to a landfill via truck, it might mean running your waste to a landfill on a train. But again, you're still sending waste to a landfill. It might mean looking at, do you need to send your waste to a landfill? Or in our case of our sample site, right, we're looking at some slightly contaminated historic fill. Is there another site undergoing remediation where we could potentially reuse that soil in a safe way? That would be a sustainable way to preserve landfill cover, hopefully to find someplace local to take it that reduces the trucking carbon footprint and the air emissions that are associated with that. Because we work on projects sometimes where there are literally thousands of trucks of contaminated soil running through quite long distances. I will say the most prominent feature of green and sustainable remediation is designing a remedy that'll be resilient to climate change. This is required in some locations, like if you're working in a waterfront area, but is not always required if you're working in an upland. Also very popular is anything that has tax incentives. So it's important for folks working in the sustainability sector to understand what incentives are out there, what regulations are pending, what's going to be coming in the future, so we can help to encourage our clients to make the right decisions from a sustainability perspective that'll also hopefully benefit them from a financial perspective. And then I wanted to, it wouldn't be a 2026 presentation if I don't mention AI. So I will say that responsible use of AI, using it in an appropriate way and not overusing it, given the reliance on water and electricity grid, is also part of a sustainable remediation. So I guess while I would have loved to come into this presentation to say that like remediation is the most sustainable industry where you could work, I think what I'll instead say is there's a lot of room for improvement. And I think as research continues around what can be done better, I think there'll be greater implementation, and hopefully we'll be seeing a lot more changes in this industry. So when we've looked at all these holistic things, right, if we go back to our sample site, we've put together this great work plan, conceptual model, hopefully it's sustainable. So what can we do? There are many, many remediation tools in our toolbox. Again, you could study this for your whole career of different remediation technologies. I've put just a few of them on the slide here. Real photos from the site are the two on the right. Firstly, we installed what's called a sub-slab depressurization system. That's the top right photo, in which we cut through the floor of the building. We installed venting piping, which collects the gases collecting under the floor, vents them safely up to the roof where they can be treated and discharged to the outdoor air safely. We also excavated the area of staining, and some of the superficial historic fill was shipped to a local landfill and was replaced by clean cover. I'll say the sustainable portion of this is we certainly are not going to excavate to 8 to 10 feet, which is where the contamination went down to. We're going to take off the top layer, which is the exposure risk. We're going to mitigate the exposure risk to anybody at this building by putting a clean cap on top of it and make sure that that cap is maintained in the long term. So there's always sort of a balance, right? You could ship the soil perhaps to a local location that might be more expensive. You could go a little further away that might be a little bit cheaper. It's a balance between cost, sustainability, timing, and what the best fit for the project is. There are in this project, we were able to determine that the groundwater contamination was not discharged from the site where we were working at. And so we didn't do any groundwater remediation, but if the spill to the groundwater had been related, we would have likely been looking at either a chemical or biological injection to which essentially induces chemical reaction in the subsurface or enhances microbial activity to degrade the contamination, break it down into less toxic end products, and eventually break down completely. So I could talk about remediation technologies for a long time, but just sort of a sampling taste of what's out there. Now, the photo on the top right is a different project where we performed an in-situ treatment with a chemical injection in which we fractured into the bedrock beneath the site. So there's a lot of different and complex remediation strategies out there. When it comes down to it, that client who came to me at the first day who said, I want to sell my business and I want to move out, I'm done with this, how do I sell my property? What he was interested in is getting to the end. So this project took about 4 years, cost about $150,000. The outcome is that he was able to sell his property, which was the most important part for him, and he was able to get fair market value for it. The building was safe for the people who were working there because the indoor air issue was mitigated. One responsibility that the buyer had to accept was that they would have to maintain this capped area that's at the bottom photo here. They would have to maintain that forever. So this was finished in, I don't know, probably early 2020s. We actually still go out to this site every year to monitor that that cap is still in place. So thinking back now at this project, where could we have done more green and sustainable remediation? I think it's a good exercise to go through for any project and to think, how could I do this differently next time? One example would be, we run this slab mitigation system that has fans that draw the air out from below the floor. Could we have run that on solar and put solar panels on the roof? Absolutely. It wasn't done at the time, but it could have been done. Do you need to remove soil for remediation and truck it? Could you leave it in place? Could you find a closer place to put it? There are questions like that that you want to think through as you design a project to understand how you're going to do it. Because I will say, you can do a remediation fast, you can do a remediation cheap, you can do it sustainably. You probably can't do all three all at the same time and really achieve all three in the way that everybody would love to. So it's about a balance and understanding priorities for yourself and for the party who's paying for the work. But ultimately, the goal of all of this is to make a safe environment where people can work, where they can play, where they can live, and hopefully impact a better tomorrow for everyone. Before I open the floor for discussion, I did want to bring to everyone's attention a couple of really great scholarship opportunities that I thought would be of interest to this group. The one on the left will be opening in the fall. This is an annual scholarship from the Licensed Site Remediation Professional Association, which I'm on the board of. We have an annual scholarship for graduate and undergraduate students in New Jersey. So if you're studying science or engineering in an environmental related field, you are eligible to apply. So I definitely encourage you to apply. We also have a really great conference every March. We love having students attend. So definitely check it out. And then currently open is the Society of Women Environmental Professionals in New Jersey. The deadline is April 10th. So if you identify as a woman and you are studying in an environmental field, undergrad or graduate, I definitely encourage you to apply. Both really great opportunities to hopefully get a little money to support your education. And with that, I will open the floor for questions. I'd love to hear what you're thinking.
Wow, that was an excellent presentation. You just painted